Hello everyone, and welcome back to the ILTA Physics Online. Today, we are going to study one-dimensional motion or straight-line motion. As the name suggests, 1D motion means an object moves along a straight line, either to the right or left, or up or down. But before we dive into new material, let's quickly review what we covered last time. In our last lecture, we talked about the 5 parameters that can describe motion quantitatively. These are the kinematic variables. They are position, time, displacement, velocity, and acceleration. Let's recall them one by one quickly. Time is treated as an independent parameter of motion, and for convenience, we usually set the initial time to 0. Position is defined as the relative location of an object with respect to a reference point. Since it includes direction like left or right, position is a vector quantity. Displacement is the change in position calculated as the final position minus the initial position. It's also a vector quantity. Distance, on the other hand, is the total path length traveled, and since it has no direction, it's a scalar quantity. When we add time into this parameter, we can define speed as distance over time. Speed is scalar. Similarly, velocity is defined as displacement over time. Since displacement is a vector, velocity is also a vector. If you've understood these formulas, you've got the key ideas. Now, let's move on to today's main topic, 1D motion. This is the simplest and most basic type of motion, so it's a great place to start. Today, we'll especially focus on 2 powerful tools for describing motion graphically, the position graph and the velocity graph. Until now, we've mostly described motion with words and diagrams, but now we'll analyze it in a more precise, quantitative way. First, let's clearly define one-dimensional motion again. 1D motion, or linear motion, is motion along a straight line. Even though it's just one line, the object can move in 2 directions, for example, right and left, or upward and downward vertically. For convenience, we usually call one direction positive and the other negative. In 1D motion, there are 2 main types: uniform motion and accelerated motion. Uniform motion means the object moves at a constant velocity, same speed and same direction. Accelerated motion means the object's velocity changes. It could speed up or slow down. First, we'll focus on cases where only the speed changes, but the direction stays the same. Later, when we study free fall, we'll deal with motion where both the magnitude and direction change. Before we get into 1D motion, let's switch gears for a second. How do we describe the motion graphically? We already know one way to show motion in a picture, and that's a motion diagram. It's just a picture that shows an object's position at every equal time step. We also learned that we can represent an object using the particle model, in other words, as a single point. The motion diagram is a very useful and intuitive picture to visually represent motion and to help us understand how an object moves. But it was a little bit difficult to use it for quantitative analysis. In addition to this, today we are going to study how to represent motion with a position graph and a velocity graph. In the bigger picture, another way to describe and explain motion is to use formulas for quantitative analysis, which we will study next time. This method makes use of the 5 kinematic variables to quantitatively express motion through actual calculations. We'll go over this one by one in detail in the next lesson. So, the first one is the position graph. The full name is the position versus time graph, and just as the name suggests, it shows the position of the object on the y-axis according to the change of time on the x-axis. If you look at the graph on the bottom right here, you'll understand it right away. On the x-axis, we have time, which is the independent variable, And on the y-axis, we have the position that corresponds to that time. Now let's use an example to understand the position graph more accurately. You need to read the problem carefully. A car starts from a point that is 10 kilometers to the left of the reference point, or the origin. Then it travels 30 kilometers to the right for 30 minutes. After that, it stays stopped for 10 minutes. Then from that spot, it moves 20 kilometers to the left for 10 minutes and then comes to a stop. The car's motion described in words above is drawn visually in the diagram at the bottom left. The car starts at minus 10 kilometers from the origin. Then for 30 minutes, it moves 30 kilometers to the right. Next, the 10-minute horizontal arrow represents that it stayed at the same spot, not moving. From there, it then moved 20 kilometers to the left for 10 minutes and came to a stop. This picture is visually intuitive and easy to understand. Now, let's draw this motion on a position graph. So, whenever you look at a graph for the first time, you should always check the x and y axes first. In our position graphs, we'll show time moving to the right along the x-axis. And for the y-axis, we'll show an object moving to the right by going up. This might sound really obvious and easy, but it's a great habit to always check the x and y axes first whenever you see a new graph from now on. For convenience in general, let's assume that the time when the motion starts is t equals 0. At time 0, the position of the object is minus 10 kilometers, so we can plot that point. This is the starting point of this motion. Then, as time goes forward 30 minutes, the car moves 30 kilometers. We show this car's motion on a position graph as a diagonal line. That's because time moves to the right, and the car moving to the right is shown by the line going upward on the y-axis. At 30 minutes, the car's position is 20 kilometers. So what you just did was represent a car's motion on a position graph. Okay, let's keep moving. Then for next 10 minutes, from 30 minutes to 40 minutes, it stayed at the same position, so on the graph the position just stays flat at 20 kilometers. A horizontal line like this also shows a car's motion. In this case, the car was stopped for 10 minutes. Then again, from 40 minutes to 50 minutes, the car moved 20 kilometers to the left, so the final position of the object is at the origin. We show this motion as a straight line going down on the position graph. As you follow the graph along with the explanation, it's easy to understand. This is the position graph, which represents the motion of the object as a graph. Yes, we can see that the position graph does a good job of showing the object's motion. But then, how can we use this graph to quantitatively describe motion? As we discussed in the previous lecture, our main interests in motion are the object's position, the distance it traveled, and its velocity. So let's check if we can find those from the graph. In other words, can we explain the car's motion that we described in words earlier using the position graph? First, let's look at the position information. From the graph, we can see that the object's initial position was 10 kilometers to the left of the origin, or minus 10 kilometers. And from the graph, the final position at the end of the motion is at the origin. The total distance traveled is 30 kilometers plus 20 kilometers, which is 50 kilometers. The overall change in position, or displacement, is from minus 10 kilometers to 0. So yes, the car moved 10 kilometers to the right. This explanation doesn't come from words, but from reading the graph. In other words, the position graph quantitatively describes the object's motion. Now let's think about another piece of quantitative information from the position graph. We want to know the velocity of the motion, which involves time. Let's recall the definition. As we defined earlier, velocity is displacement over time. Since our position graph shows displacement, we can calculate velocity. In other words, the slope of the position graph at each point represents the velocity. When I say each point, It could mean our focus is on time or on position. So, in any case, the slope gives us the velocity at that point. And of course, the sign of the slope indicates the direction of motion. Here's one tip. When doing quantitative analysis of motion, is it better to calculate velocity, which is a vector quantity, or speed, which is a scalar? I trust that you remember the definitions of velocity and speed and their differences. Earlier, we explained that speed can be thought of as the magnitude of velocity if the direction doesn't change. So, in an example like this one where the object changes direction from right to left, it's a good idea to break the motion down into parts with the same direction and analyze each section separately. Remember how in the last lesson, we ran all the way around a track, but the velocity came out to be 0? That example will help you understand. Now, let's apply this idea and calculate the velocity for each section. Looking at the position graph, the car's motion can be divided into 3 intervals with consistent direction. The first interval moving to the right, the second interval standing still, and the last interval moving to the left. In terms of time, these are from 0 to 30 minutes, from 30 to 40 minutes, and from 40 to 50 minutes. Now let's calculate the velocity for each interval. Since velocity is defined as displacement over the time interval, the numerator, displacement, is the final position minus the initial position, which is 20 minus 10. The denominator, time interval, is the final time minus the initial time, which is 30 minus 0. So the velocity in the first interval is plus 1 kilometer per minute. Again, since velocity is a vector, I added the plus sign to explicitly show the direction. In other words, in the first interval from 0 to 30 minutes, the object was moving to the right with a velocity of 1 kilometer per minute. Next, in the interval from 30 to 40 minutes, the car stayed at the same spot, so the displacement is 0. Therefore, the velocity is 0 kilometers per minute. In the last interval, from 40 to 50 minutes, I'd like you to carefully think about the signs and calculate it yourself. Reading the positions from the position graph and working out the sign properly, you get minus 2 kilometers per minute. Since the velocity is negative, that means in this section, the car was moving to the left with a speed of 2 kilometers per minute. So now you see how precisely and quantitatively the position graph represents the object's motion. The velocity graph is simply a graph of the velocities we calculated from the position graph. The full name is the velocity versus time graph, and as the name suggests, it shows velocity on the y-axis versus time on the x-axis. Based on the car example we already calculated, the velocity graph of this motion is as shown on the right. The quantitative calculations are on the previous slide. This velocity graph visually and intuitively shows the velocity information of the motion. Since this is a repeated explanation, we won't go over each section again. But one thing to be careful about is that velocity is a vector, so it can take negative values, which mean motion to the left. Since negative velocity isn't a quantity we usually use in daily life, you need to pay special attention until you get used to it when studying physics. Another feature of the velocity graph is that the area under the graph, with respect to the x-axis, represents displacement. Again, let's be careful. Displacement is also a vector, so it can be positive or negative. A negative displacement means the object moved to the left. As shown in the figure on the bottom right, for the whole motion of the car from 0 to 50 minutes, the areas with respect to the x-axis are 30 and minus 20. So the total displacement is 10, which means the motion ends at a point 10 kilometers to the right of where it started. This same total displacement can also be seen from the position graph we discussed earlier. The car started at minus 10 kilometers and ended at 0, so it moved 10 kilometers to the right in total. Finally, let's briefly explain instantaneous velocity before we end today's lecture. Because we learned how to represent an object's motion with a position graph today, we can now define it. Instantaneous velocity is defined as the velocity of a moving object at a particular instant of time. If we think about a position graph like the one below, as we said earlier, the slope of the position graph shows the velocity. In the case of motion where the position changes smoothly with time, we can think of this as the average velocity over an extremely small time interval, which we call the instantaneous rate of change. From a geometric perspective, it can also be defined as the slope of the tangent to the position graph at that time. Of course, instantaneous velocity is also a vector, so its sign shows the direction of motion. Instantaneous speed is defined as just the magnitude of the instantaneous velocity without considering direction. Today, we studied position graphs and velocity graphs, which are very useful methods for visually and quantitatively describing the motion of an object, at least in simple one-dimensional motion. These graphs not only precisely describe the object's motion, but also give us information about various quantitative physical quantities. Next time, we'll calculate motion in a more quantitative way using formulas. Good job today.